All right, we are going to go through example 5.70. So I'm just going to read it for you guys. A procedure for determining the thermal conductivity of a solid material involves embedding a thermocouple in a thick slab of the solid and measuring the response to a prescribed change in temperature at one surface. Consider an arrangement for which the thermocouple is embedded 10 millimeters from the surface that is suddenly brought to a temperature of 100 degrees Celsius by exposure to boiling water. If the initial temperature of the slab was 30 degrees and the thermocouple measures a temperature of 65 degrees Celsius 2 minutes after the surface is brought to 100 degrees Celsius, what is its thermal conductivity? The density and specific heat of the solid are known to be 2,200 kilograms per meter cubed and 700 joules per kilogram Kelvin. Oops, sorry about that. Okay, so we are just going to start off by writing our givens. So we know that the distance equals 10 millimeters, which equals 0.01 meters. We know T initial equals 30 degrees Celsius. We know T2 equals 100 degrees Celsius. We know the density equals 2,200 kilogram per meter cubed. We know the specific heat capacity equals 700 joules per kilogram Kelvin. And then we know that T equals 0.01 meter at 100 seconds. It equals 65 degrees Celsius. This is like where the thermocouple is. So just to kind of give a little picture of what we're looking at. This is kind of how I'm picturing it. And then we have a little thermocouple. This distance is that 0.01 meter. That is the thermocouple, and then this is boiling water. Okay, so if we assume a semi-infinite medium, we know from just our textbook that T of xt minus 2, T2, all over T initial minus T2 equals this. So if we fill all this in, we get 65 degrees Celsius minus 100 degrees Celsius all over 30 degrees Celsius. Okay. And we do a little bit of math. So in table, if you go to table B.2, we know that Z equals X over 2 alpha T. And then we also know this just from our calculations. So from that table, you're able to do a little bit of linear interpolation. Therefore, you get a Z value of 0.477. And again, this is if you go to table B.2. So then, just do another page. So from this, we know that, again, Z equals X over 2 alpha T, the square root of that. So we know that 0.477, that value that we just got from B.2 table, equals 0.01 meters over 2 alpha 20 seconds square root. And then if we rearrange that, we get that alpha equals 0.96 times 10 to the negative 6 meters squared per second. So we don't want alpha, we actually want thermal conductivity. So we all know that alpha equals K over rho Cp. Rearrange that for K, we get K equals alpha rho Cp. So now we know that K equals, we just solved for alpha, 0.196 times 10 to the negative 6 meters squared per second. We were given density, and we were given specific heat capacity. And then if we just do a little bit of math in our calculators, we get 1.41 watts per meter Kelvin. All right, and I'll just zoom out a little bit so you can see all of those calculations. And that is the video for 5.70. Thank you.